In our last lesson, we talked about propositions, statements that are either true or false, but not both. We talked about connectives between propositions, and we used truth tables where we can denote a proposition P. And since we know that it has two possible values, either true or false, we can use that to deduce how various propositions being combined via connectives, how their corresponding truth values are based on their P and Q values. So specifically, we looked at the connectives and, or, and not. And in the homework, you ran into exclusive or, which our textbooks denotes by plus. Now, with and, we have that P and Q, its truth table depends on the validity of P and Q both being true. And so if both of them are true, we have that P and Q is itself true. Whereas if one of them is false, then P and Q will automatically be false. And that's what we have here. So here we have false, false, then we have false for Q in this entry, false for P in this entry, and similarly we have false for both of these. So this will be false. Whereas with or, P or Q, we have that is going to be true if one of P or Q is true. And so now we have that since in the very first row, both P and Q are true, and in the next two rows, we have that at least one of P or Q is true, so we have that these are true. And finally, we have false for the last entry, since both P and Q are false in that last row. But now with exclusive or, we want to eliminate the possibility of P and Q both being true. And since that happens in the first row, now we have a false here, and then true for the next two, and finally false. We talked about what it means for statements to be logically equivalent, and we proved the first of De Morgan's laws. And so I'm going to go ahead and now just run through the argument for the second form of De Morgan's law. And just to get us again into practice, whenever we're trying to show that two statements are logically equivalent, we want to go through and compare the truth tables. If their truth tables agree, then the corresponding propositions are logically equivalent. And the way we want to do that is by putting in all the steps necessary in between to build up to it. Of course, we can usually sometimes do shorthand and get to our truth table quickly. I'm going to go through and just lay out every step here. And so we want to go and find not P or Q. And so first, let's go ahead and do P or Q. And then we're going to do not P. And then not Q. And finally, we're going to do the two that we want to compare. And so now here we have not P or Q and not P and not Q. And so again, with P or Q, we're going to have that this here will be true, 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 and then finally false. But now with not P, we're just negating the entry for P. So this will be false, false, true, true. And not Q would be false, true, false, true. And now we are left with the last two columns, which correspond exactly to what we want to show, that these are logically equivalent. So now both of these should match up for this to be true. And so we see that P or Q, if we take not of that, we're just negating all the entries here. So this will be false, 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 true. And similarly, we're doing not P and not Q. And so now we're looking at both of these two columns. And what we have here is that this here will be false, false, and false, since we have at least one false in each of these corresponding columns. And then finally, the last one is true. And so here we have false, false, false. And then finally, in the very last row, we have that both not P and not Q are both true. And so this here will be true. And now we see that both of the truth columns are equal. And now we have, and so we can conclude, since not P or Q and not P and not Q have the same truth tables, we conclude that they are logically equivalent, which I'll write in shorthand as this notation here, that they're logically equivalent. We also have commutative laws and associative laws. So if we have and, so P and Q is equivalent to Q and P. And similarly, we have that P or Q is equivalent to Q or P. We also have associativity. And it's crucial that for the associativity we have that we are talking about the same connective. So here we have P and Q and R in parentheses. And that will be the same as doing P and Q first and then having and R. And similarly, if we have ors, then we have P or the proposition Q or R, and that will be equivalent to switching the parentheses to P or Q and then or R. And as I mentioned, it is crucial that the connectives are the same for the associative laws to hold. Because if they don't match up, then we have a distributive law. And so specifically we have and then inside the parentheses we have or. We are going to have a distributive property. This will become P and Q, and then or over here, and then P and R. And similarly, we have that P or parentheses Q or R, Q and R, is equivalent to then P or Q, and then the and comes here, and we have P or R. We have this one right here. And this leads to the following sort of views of notation. So whenever, let me just write this over here. So if we have P or Q and R, so here we have all the same connectives. We're now looking at this associative law right here. It is common to simply write P or Q or R. And similarly, if we have then P or Q or R, we write we drop the parentheses and we write P or Q or R. Here, we implicitly assume the associative law. But this is an abuse of notation, which is quite common in math. We know that in this case we have the associative law, so we don't have to add those parentheses. And so whenever we drop the parentheses, it is implicitly understood that the associative law holds. But we need to be very careful when doing so, because we can't drop the parentheses all the time. And so, however, if we have P and I'm now dropping the parentheses, Q or R, this is ambiguous, since the associative law does not hold. So usually I will go ahead and opt to write the parentheses, just for clarity, just to avoid any of the situations that are arising here, but it's just something to be mindful of. If you drop the parentheses and you have different connectives, then we have the distributive law holds, and so this is not well defined, this is ambiguous. And so this here does not make any sense in this context. We also have other laws that we can show that are logically equivalent using the same argument via truth table. So we have the idempotent laws, distributive laws, absorption laws, And finally, the double negation law, which says that if we take not P, then that is the same as P. One of the questions that arose during our synchronous session was the following. If we have the statement P and not P, is this a proposition? And the answer is yes. Because when we talk about propositions, all we need is that the statement is either true or false. It can't be both true or false, or both false. And so in the case of P and not P, if we do a truth table, then we have P is either true or false, since it is a proposition, and then not P consequently has to be false, true. And so when we do P and not P, we always have here that this is false. And similarly, if we were to now take this a similar construction, but now we do P or not P. Now in this situation, we will now get that in this case we always have true, since one of these entries in these columns is that it's always going to be true for at least one. And so here we have true and true. And so these are examples of statements that are known as contradiction and tautologies, respectively. And so this here's what we call a contradiction. It is always false. And now here's what we have, a tautology. Now more formally, we can go ahead and define contradiction and tautology as follows. We say that if A, and so I'm going to switch to the letter A, so if A is a proposition, formed from other propositions, and let's go ahead and call those propositions, say P, Q, R, so on and so forth. So these are all propositions using logical connectives. Then we say that A is a tautology if A is true for every assignment, bad handwriting, assignment of truth values for P, Q, and R, and so on and so forth. And similarly, we say that A is a contradiction if A is false. And then we just the same exact statement. If A is false for every assignment of truth values for P, Q, and R. And so in this notation, in the case of contradiction, the notation A is referring to P and not P. And then the P, Q, and R, we can think about P just our P here, and the not P is now our Q. And so we have that A is formed via logical connectives by P and not P. And it is always false regardless of the truth value assignments for both P and not P. But now this holds more generally. And so this is what we define to be tautology and contradiction, respectively. So next, let us do an example of this. So that P and Q be propositions what is P, and then we're going to do P or not, and we're going to have Q or not Q equivalent to. So can we write this in a shorter way? And the answer is yes, Because in this case, since Q is a proposition, we have Q or not Q, but we just saw that over here. That's always a tautology. But then, if we have a tautology here, this is always going to be true, regardless of the truth value assignments for Q. And consequently, if we take the negation of a tautology, if this is always true, then the negation is always going to be false. And so this here will be a contradiction. But then P, or not Q, since this here is always going to be false, its value will just depend on P. And so this will be logically equivalent to P. Since now we have, in this situation, we have P, and I'm going to write here for a so P or C for the contradiction. And so of course we're just going to have that if P or C, so this is going to be true, and then if P is false, then the contradiction is false, so then this statement will be false. And so we have that this is logically equivalent to P. And so this leads to the following laws that the book calls tautology laws and contradiction laws. And so what we have is that if we have P and a tautology, that is always going to be equivalent to P. And similarly, if we have P or a tautology, then we are always going to have a tautology, since the tautology is always true. And we just saw an instance of not a tautology, that's a contradiction, so we saw that so that's what we just did for the previous example. And in the same manner, we have contradiction laws. If we have P and something that is always false, we're going to get back false, regardless of what the truth value assignments for P are. And if we have P or a contradiction, which is what we just saw, that is going to be equivalent to P. And finally, if we negate a contradiction, we get a tautology. So next we are going to go ahead and define the concept of a set. So sets are something that you have already encountered in your prior math courses. But what are they at their core? And its definition is as simple as we can hope. By a set, we mean a collection of objects. A collection of elements. I said objects, but same word here. Elements or objects. But now this definition is very general. And one consequence of having such a general definition is that we don't necessarily need to have mathematical concepts in order to have a set. So for example, we can have the set that contains the US, Mexico, and Canada, as well as a set, of course, that contains 1, 2, 3, 4, or all the positive integers. 1, 2, 3, and then just continue onwards. And so these are all examples of sets. And the question that I want to pose to you all, which we will discuss further at the beginning of our next video, is the following. So given any collection of elements is there a set that contains them? And so this is something we're going to investigate in further detail in our next lesson, but this is just to start pondering. Now, moving forward, let's go ahead and discuss the notations for sets that we have already experienced in the past. So for example, the real numbers. So the real numbers, it's those elements, x, and I'm going to use this notation bar. X is a real number. And now this bar here is such that. And oftentimes as we go through the course, I'm going to abbreviate such that to just s dot t dot. And whenever we're using a set, we'll just use this bar notation. So x bar. So this will be read x, the real numbers is the set of those x's such that x is a real number. We also have the rationals, where now x such that x is a rational number. We also have the complex numbers, x such that x is a complex number, but here we can do much better because we can explicitly describe. And so here we can go ahead and rewrite this as those numbers of the form a plus bi such that a and b are themselves real numbers. And so here we're using the notation in. So whenever we say a is in R, is that a is in the set of real numbers. And so we have this notation. We also have the integers. And so we use the notation, the Mathbode Z. And so this is German, it comes from the German word for numbers, Zahlen. And so this is just a collection of those numbers, just all the negative numbers. And so I just do -4, -3, -2, -1, 0, 1, 2, 3, 4. And then we just continue onwards. And so these are the integers. Now the next set we're going to introduce, and this is a controversial one in terms of which book you use, is the concept of the natural numbers. And so our textbook starts at 0, so we have 0, 1, 2, 3, so on and so forth. And so these are the natural numbers. And the reason I say that this is a controversial set is that it is one of those things that varies from book to book. And depending on the discipline, it's important to know if your numbers include 0 or not whenever you refer to natural numbers. So for example, in number theory, we don't include 0 as an element of the natural numbers, whereas in other areas of mathematics, such as in logic, we do include 0. And that is what is happening in this case, where we're going through set theory and logic, and the natural numbers will be defined to start at 0, since it makes some of the terminology and concepts that we're going to discuss later easier to follow. So on a historical note, the reason that I say that the natural numbers, the way that including 0 or not is controversial, is that the natural numbers originally were defined in number theory. And the reason why 0 is not a natural number is that at least in Western cultures, the number 0 did not appear in the literature until 1598. If you go back to ancient Greece or to the Roman Empire, they did not have a concept of 0 in the mathematical sense. But it's crucial to emphasize the Western world. Because in India, going back to 200 before Common Era, Pingala had already introduced the number 0 in the same way that we use 0 today, in addition to discovering the binomial coefficients, which in the Western world we refer as Pascal's triangle. So the numbers that occur when we look at the expansion of a plus b squared, a plus b quantity cubed, a plus b quantity fourth. So when we look at Pascal's triangles, those numbers were not due to Pascal, but actually date back to Pingala, who came up with them through his work on Sanskrit. So that's an interesting thread if you're interested in pursuing, that this notion of how math corresponds to poetry. And so Pingala was an Indian poet who, in trying to find the various different ways that we could make poetry could be done in Sanskrit in terms of syllables, came up with the binomial coefficients as well as the Fibonacci sequence, a millennia prior to their discovery in the West. So let us return to notations of sets that we are used to. In calculus, we are used to using the interval notation, so we do 0, 1. What we really mean is the set of real numbers. So I'm going to write this now as x such that x is a real number, and then now I'm going to use the inequality. 0 is less than or equal to x, which is strictly less than 1. And so that's another way that we use set notation. We have used set notation previously. Now, building on what we just did with complex numbers, we could ask the following. So question, is Q equal to A over B, where A and B are integers, and B is not equal to 0? Because when we look at the rational numbers, we're looking at fractions of integers. So this seems like a natural definition, because over here, when we define the rational numbers, and I just realized I forgot to close the set, when we define the rational numbers, we just said x is a rational number. Whereas with the complex numbers, we were able to build this set in terms of the real numbers. So can we just define the rational numbers to be this? And the answer is no. And the reason is that we have not defined what it means for two sets to be equal. And that's our next definition. So two sets are equal if they have precisely the same elements. And so now, one thing about this, in terms of terminology, is that if we have the sets A, B, C, where these A, B, and C are distinct, this here will be the same. So I'm going to write this as an example. This will be the same as just the reordering, B, A, C. Or we can also have that this is equal to C, A, B. Of course, this comes with no surprise. All we did was just change the order. But here's how we're using the concept of equality. And in the next lesson, we're going to introduce the notion of biconditional. And so this is the notion of if and only if. And then I'm going to go ahead and then redefine equality in terms of a biconditional in the next lesson. But for now, we're going to have it just in terms of this precisely having the same elements. And so the precisely having the same elements means that if we just go ahead and write C, 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 A, A, and then B, B, now we have repeats. And because we have repeats, then we still have that these two sets are the same, because we do have C is in here, A is in here, and B is in here. And similarly, we have everything in reverse. Every element in here is contained in each of these. And so we do have equality. And so we can go ahead and put in the same exact element into our set, but it does not give us the same, we can add all these values in there, but it does not change the set itself. It's still the same exact set. And because of that, we have that Q is not the same as A over B. The reason is that in the set here, we have the 1/2 and 2/4. These are contained in the set A over B. A and B are integers, and B is not equal to 0. So these are in here, and they are in the set not equal. In this set, 1/2 and 2/4 are distinct elements. However, in the rational numbers, in the rational numbers, we have that 1/2 is equal to 2/4. And so as a consequence, we do get that these are not the same exact set. And it's one thing that we will do later in the course. So for later, we will define Q as a set built from the integers. Via what is known as an equivalence relation. Topic of equivalence relations. And so this is something that we will be discussing around week 4 and 5. And with it, we will be able to build the rational numbers as a set and have it in somewhat closer form to this. And the notion of an equivalence relation is that we want to emphasize this 1/2 and 2/4 being equal. And so we see that that's what's failing in having the rational numbers being defined like this. And through an equivalence relation, we will be able to impose that condition where we have a set with an additional condition where now 1/2 is equal to 2/4. And more generally, we have that A equals B, A over B is equal to C over D, if and only if AD is equal to BC. And so this is something that we'll come back to later. So this is more to give a preview of what is to come. So let's go ahead and just discuss a couple more notions about sets. And so one set that we had that doesn't tend to pop up in prior math courses prior to structure is what is known as the empty set. And so this is the set containing nothing. And so this is if we were to write it in set notation, we'll just simply write it like this. Symbolically, we write this as the empty set. This is also referred to as the null set. Now, we have a notion of finite and infinite. And so definition, a set is finite if it is empty, or can be matched up with one, two, three, and then we go counting to all positive integers until we get to some n. For some n in the positive integers. Now here, let me go ahead. So here I'm using new notation. So here the z plus refers to the positive integers. Now, there is some ambiguity to this definition, because what does it mean to match up? Now, later in the course, we're going to come back and define finite in a rigorous way using the material that we are going to build. But for now, we are relying on our intuition. But part of our course is to get rid of that argument of relying on intuition and making it precise. How do we define finiteness without having to rely on these intuitive concepts that we are invoking when we say we match up with a set 1, 2, 3 all the way to n? Because in this case, we have, if we look at A, B, C, what we want to here think about matching up is that we are matching each element appearing in the set A, B, C with the numbers. So we can match up with A with 1, B with 2, and C with 3. And now we have that this is a finite set, so it matches up with our intuition. But one thing that we are going to do later in the course is return to this definition and make this rigorous by the notions of functions between sets. And we are familiar with functions from our previous math courses, and so what we are going to do is think about defining a function F, where we go from the set A, B, C, and we go to the set 1, 2, 3. And so now the input here is f of A goes to 1, f of B goes to 2, f of C goes to 3. And we're going to introduce the notion of a bijection, a function that is both one-to-one. We're going to be also using the word injective. And so this is a word that you have seen in calculus, as well as the situation of the function being onto, or how we will be referring to it later as surjective. And so this is just to give a preview of how we're going to come back and define these concepts that are intuitive right now, but we can make it precise by discussing functions. Now, if with this intuitive definition of finite, we can define what it means to be infinite by just saying a set that is not finite. So a set is said to be infinite if it is not finite. Now, let us return back to the topic of propositions and statements. So let's go ahead and consider the following. 3 is an odd integer. This is a true statement. It's a proposition. But what if we wanted to now replace this 3 with an x? So we can have now x is an odd integer. So we can go ahead and write this statement now as q of x. Now note that this is still, if we plug in values of x where x is an integer, we get back a proposition. In the case of 3, we have that is exactly p. Q of 3 is the statement p. But now, this is still going to give us a proposition once we plug in an integer x. If we plug in x equals to 2, we get back that 2 is an odd integer. That's a false statement. And so we now can build propositions by having this dependence on a variable. Once we plug in, we get a proposition back. But we also have that this is giving us a set. We can now consider what are those x's that make this true. And so now that will give us the following set. So we have x such that x is an integer that is odd. We could also write this in another way of writing this. I'm going to write this here as follows. X is an integer such that x is odd. We could also write this as x such that x is an integer and x is odd. And so these are equivalent ways of writing it. The reason I'm writing it in this way is that we want to specify that x is an integer. Because if we simply write x such that x is odd, well, what is x? We have a notion of a function being odd or even. So is x a function? And so we want to make sure that we specify what x is and not have it rely on the context. And so in this case, we will not be writing it in this way, but rather specifying that we are dealing with integers. Now, this here is the set that makes q of x true. So note that x in Z such that x is odd is the set of elements that makes the statement q of x true. So in our book, there's actually a term that they use to define this condition that we must satisfy to be in the set. And so it's what they refer to as the elementhood test. So whenever we have, so in this case here, this here is referred to in our text as the elementhood test. In that to be in this set here, we must have an integer x, where x is odd. And similarly for the sets that we already considered, to be in these sets, we must satisfy this condition. And so the book refers to this as the elementhood test. And so with that, let's go ahead and look at the next definition. And so now what we have been discussing with our statements here for Q of x, we also can say that in this case, the set that we constructed here is the truth set for Q of x. So more specifically, the truth set of a statement P of x is the set of all values of x that make P of x true. And so in other words, it is a set where we now use the elementhood test. And so it's just a condition that is satisfied. And so we have x such that P of x. For our next lesson, we are going to continue discussing sets, but also operations on sets. And also discuss the history of how sets were introduced, because it's actually a very recent topic, dating back just to 1874. So next time we're going to talk about the history of set theory and how it arose. And we're also going to come back to the question at the start of today's lesson on sets, namely, given any collection of elements, is there a set that contains them?